Hello everyone, my name is Junso Hwang. Today, we would like to present our study on non-volatile chart-trap flash memory with solid-phase diffuse junctions. In this work, we applied PSG doping to the CTF structure, aiming to enhance both the electrical and memory characteristics of the device. This presentation consists of 4 parts. We begin with CTF memory and solid-phase diffusion, followed by device fabrication. Next, the electrical and memory characteristics will be discussed, and we close with the conclusion. Non-volatile memory is a key technology that preserves data even when the power is off, and it is essential in devices ranging from smartphones to everyday electronics. With the increasing demand for data, the development of next-generation non-volatile memories has become critical as the foundation for future technologies such as AI, autonomous driving, and the Internet of Things. Flash memory is a representative type of non-volatile memory, which means it can retain data even when the power is off. It is widely used in storage devices such as SSDs and smartphones. Flash memory can be largely divided into 2 types, floating gate flash and chart-trap flash. In conventional floating gate flash memory, the polysilicon floating gate stores charges, and the threshold voltage shift is used to distinguish between 0 and 1. However, as device scaling continues, floating gate structures face serious challenges such as cell-to-cell interference, oxide leakage, and defect sensitivity. To overcome these limitations, chart-trap flash memory was introduced. It uses a nitride trap layer instead of a conducting floating gate, which provides less interference, lower leakage, and scalability for 3D integration. Also, with the scaling limit of 2D structures, flash memory has been extended into 3D stacking. However, as the stack height increases, defects from ion implantation critically affect device performance. Therefore, solid-phase diffusion doping has re-emerged as an alternative. Since it is diffusion-based, SPD can effectively dope sidewalls and deep regions of complex structures such as FinFET and GAA, while reducing shadowing effects. In addition, SPD offers simpler processing and lower cost, making it attractive for next-generation 3D memory fabrication. In our previous semester, we fabricated PN diodes using the SPD technique. In this process, PSG was spin coated on the P-type substrate and then diffused into it through thermal annealing. As a result, we successfully formed PN junction diodes that exhibited very promising electrical characteristics. This device structure is based on a soy substrate. From the bottom, it consists of a silicon layer, a buried oxide, and a polysilicon channel. On top of the channel, an ONO stack is used as the gate dielectric, and finally, the gate electrode is formed on the top. In our experiment, PSG doping was applied to the gate and polysilicon region. The process temperature was split into 4 RTA conditions: 800, 850, 900, and 950 degrees Celsius, with the goal of identifying the optimal condition that provides the most stable and enhanced memory characteristics. Also, our goal is to demonstrate that SPD-based doping enables stable and reliable performance, showing the potential of this device as a next-generation, high-speed non-volatile memory. This page shows the transfer curve data of the device under different PSG doping conditions. The results indicate that at 950 degrees Celsius, the device exhibited the widest hysteresis window, the lowest threshold voltage shift, and stable charge storage. This is attributed to dopant activation at high temperature, which improves trap density and channel conduction. In contrast, at 800 degrees Celsius and 850 degrees Celsius, insufficient charge trapping led to narrow memory windows, suggesting weaker retention. In addition, when varying the active width, the 10 micrometer devices showed the widest memory window and the most stable threshold voltage shift, confirming that sufficient channel width enhances both device operation and memory performance. Therefore, The optimized PSG doping condition was identified as RTA at 950 degrees Celsius for 30 seconds, under which the CTF device demonstrated superior electrical and memory characteristics. At 950 degrees Celsius, the PSG-doped CTF device showed the highest drain current and a stable memory window. Across all active visits, 950 degrees Celsius produced the maximum current and the minimum current, giving the best on-off ratio. In contrast, 800 degrees Celsius showed poor switching due to weak dopant activation, while 850 degrees Celsius and 900 degrees Celsius were only moderate. Thus, the optimal condition was RTA 950 degrees Celsius 30 seconds, with the 10 micrometer device showing the best switching and memory performance. This slide shows the program and erase operation characteristics of a CTF device with PSG dop source and drain regions. We used an SMU probe and a connection board integrated with the EasyExpert LabVIEW program and a MUX to measure the transfer curves. Stress times ranging from 1 microsecond to 10 milliseconds were applied to the gate. The drain current was measured while sweeping the gate voltage from -1 volt to 6 volt in 0.1 volt steps. The results showed stable program operations at 5 volt, 6 volt, and 8 volt, and the most stable erase operation at -6 volt. So, our measurements confirm that the CTF device reliably performs basic program and erase operations. This also verifies the successful formation of the source and drain doping using the SPD process. This slide shows the results of our retention test conducted to verify the non-volatile memory characteristics of the device. We set the program voltages at 5 volt, 6 volt, and 8 volt, and the erase voltage at -6 volt. Measurements were taken from 0 to 10,000 cycles with a 100 microsecond period, specifically at 20, 50, 100, 200, 500, 1,000, 2,000, 4,000, and 10,000 cycles. The data from up to 10,000 cycles revealed that charge loss decreased as the applied program voltage increased, in the order of 5, 6, and 8 volts. This confirms that the ONO layer in our designed CTF device effectively traps charges and that the erase operation functions correctly. Therefore, the retention test successfully verifies the device's potential as a memory element. This slide presents the results of the endurance test, which we conducted to evaluate the long-term reliability of our device. The device maintained stable charge trapping. The threshold voltage shift remained below 1 volt in all cases. Therefore, it was confirmed that SPD-based source drain doping can be stably applied to CTF devices, providing excellent long-term reliability. In this study, we implemented a CTF memory transistor using SPD-based doping and an ONO step as the charge trapping medium. At 950 degrees Celsius RTA with a 10 micrometer active width, the device achieved the highest on-off ratio, showing excellent switching performance. In addition, we confirmed stable program operation at 5, 6, and 8 volts, and stable erase operation at -6 volts. For the retention characteristics, we observed that a higher voltage resulted in reduced charge loss. Furthermore, in the endurance test, even after 10,000 cycles, the threshold voltage shift remained below 1 volt. Therefore, the CTF device with SPD-based doping demonstrates stable and reliable performance, and it shows strong potential for next-generation high-speed non-volatile memory applications. Thank you.